Good morning, good morning, good morning. Hope all is well. Hope everything's going all right. All right. Looks like everybody's in. Okay. So we knocked out what 1-3 last class. So we'll look to get into 1-4 today. Any general questions before we get rolling? Everybody doing okay? All right. All right. So we're looking at complex numbers today. Okay. So not sure if we've done it in this class before, but in the past, before you actually start talking about complex numbers or imaginary numbers, whenever you take the square root of a negative, you will write not a real number. Well, so that segues us into this thought process. When you don't have a real number, it is considered imaginary. And that imaginary unit is going to be represented by I, that italicized I. So the square root of -1 is going to be represented by I. Sorry, I'm trying to get these people in here. Okay, so where does that come from? Well, when we take the square root of 25, the answer is 5 because 5 times 5 will give us 25. Same thing with the square root of 81. That's going to be 9 because 9 times 9 will give us 81. And then square root of 121 is 11 because 11 times 11 will give us 121. So any number times itself. Well, what you're saying is when you take the square root, you're saying what number times itself twice will give me the number that's under the radical. So now when I look at the square root of -25, there's not a number times itself twice that will give you a -25. You know, when we look at -5 times -5, that would actually give you +25. So really, if I wanted, I could let -5 be the answer here for the square root of 25. It's just that whenever we're looking at those values, we want the positive representation of our numbers. So that's why we don't consider it a negative value. So there's not a number that will give me -25 when I multiply it times itself twice. So whenever I have a square root of a negative, that means there is an imaginary number out there that we could use that would represent that. Somebody said, this is where we started. For somebody that said, this is the beginning of the notes, titles right here. So you haven't missed anything. I was just, introducing the top section. So, so taking the square root of a negative, we have to represent it by I. So whenever we have the negative under the radical, we have to represent it by I. So if I have the square root of -25, and you don't always have to break it down this way, just showing you how you should be processing it mentally, you do the square root of 25, which is 5, and then the square root of -1 is always going to be represented by I. And the same thing happens here. Square root of -81 is going to be 9I. Square root of -121 is 11I. All right, so whenever you're taking the square root of a negative, I should be involved as a part of your final answer. All right, any questions on that? Okay, so now if you're taking the square root of something that's not a perfect root or perfect square, you are expected to simplify that as much as possible, if possible. So looking at the square root of 18, I would take that 18 and break it down, looking at the factors of 18, asking myself, can I take the square root of any of the factors? Is there a perfect root when it comes to one of the factors of 18? Notice I have 1 times 18, 2 times 9, 3 times 6. I will not use 3 times 6 because I cannot take the square root of 3 or 6. So what I would use is 9 times 2, take the square root of 9, which is 3, and leave the 2 under the radical. So 3 square root of 2 would be the most simplest way of representing the square root of 18. So those type of things, whenever you're dealing with the radicals, dealing with square roots especially, you are expected to go that next step if you don't have a perfect square.
So
Mhm.
why didn't you use 3 times 6?
Because you can't take the square root of 3 or 6.
Okay.
So we use the 9 times 2 because I can take the square root of 9, which gave us 3. All right. So then looking at the square root of negative 24, we will look to break that up in the same fashion with the same thought process. What factor of 24 can I take the square root of? And I will use 4 times 6 because I can take the square root of 4. Only difference, the main difference here is that there's a negative involved, so we have to include that as a part of our simplification process. So I break it up into negative 4 and 6. Negative 4 times 6 is still negative 24. Square root of negative 4 is 2i. And then I leave the 6 under the radical. Then you just leave it. If you can't break it down any further, can't take the square root of any of the factors, then you would just leave it under the radical. So if I just had the square root of 17, then that's all it would be is the square root of 17. I can't break up 17 into anything. Yep. But you are expected to evaluate to see if you can go any further. Also down here, notice I have the answer represented, 2 different ways. Doesn't matter which one you use, still should be the same answer, even in my math lab. I normally like to use this way, 2i square root of 6. But it's only preference. Just make sure that you do not, if you use this one here, that you do not extend the radical over this I, or it will be considered wrong because that's not right.
I have a quick question.
Mm-hmm.
Because for the last example, the 2 is outside of the square root, that's to imply that the 2 is going to multiply the 6?
Yes. Well, 2 is
Okay.
multiplied by the square root of 6.
Of 6.
Mhm.
Oh, shit. Okay, what does that mean?
Well, you see,
Multiplied by the square root of 6.
no, the square root is still here. Well, you said 2 times 6. I just want to make sure that you still was including the square root as a part of that process. You know what I mean? Because the square root is not going to disappear because we couldn't apply the square root to the 6 evenly. So when you said 2 times 6, I just didn't want you to think it was 2 times 6, but it's 2 times the square root.
Okay, and it's the square root of 6 is because you can't further simplify
Right.
the square root of 6.
Right, because remember that was the
Okay.
square root of 4. That's how we got to 2. But and that's why that disappeared. But we can't fully simplify the square root of 6. Yep.
Okay, so it's like 2 imaginary number or imaginary, not a real number, right? Square root of 6.
Yeah.
Okay, I thank you.
Yeah, you're fine. You're fine. Not a problem at all. So all of that, like you said, is multiplication. All right. And this last one, I was just playing with the breakdown. Somebody had asked me, I don't know if anybody asked me anything, but I was just showing you that even if you didn't get the largest number that could be simplified, if you continue to break it down, you still get to the same number. So if you look at square root of 500, the largest number that you can break down is a factorization of 500 that can be taken the square root of is 100. So 5 times 100 is 500. Taking the square root of 100 will give you 10. So the answer is 10 square root of 5. Can't do anything with the 5, you leave that under the radical. But let's say you didn't see 100, but you saw 25 in the 500 and you broke it up into 25 times 20. And that'll still give you 500. If you break down the 25, square root of 25 is 5. But the square root of 20 can still be broken down further. You can use 4 times 5, square root of 4 is 2, then 2 times 5 is 10. So either way, you'll still get 10 square root of 5. So I was just showing you that even if you didn't see the largest number, as long as you see a number that can be broken down, you can keep breaking down further and eventually get to the same answer. So that's all I was doing here. Still the same process, just showing you that you don't necessarily have to pull the largest number out at first. But if you keep breaking it down, you get the same answer. All right, so just so you only use I if you can't square. No, you use I if you have a negative under the radical. That's when I comes into play. But if it's positive, you never use I. Okay, So just like we had here with the 18, we didn't use I. It's all about if you have a negative under your radical. Yep. Somebody said in the chat, negative square roots are imaginary because they can't really occur. Yep. All right. So imaginary is a part of what we call you can well I say it like that. Imaginary numbers is a part of what we call complex numbers. But your complex number is going to involve a real part and an imaginary part. So when we have a plus bi, the standard form of your complex number will be a plus bi. When you have your real part first, then you write your imaginary part. That is your standard form. So if you were to write the imaginary part first and then the real part, and they ask you to write it in standard form, all you need to do is switch the numbers around. But the standard form is your real part first, then your imaginary part. So over here, just examples of complex numbers. 2 plus 5i, -1 plus 3i, 7 minus 10i. Then the number 8 can be written as a complex number. If you write 8 plus 0i, and then -12i can be written complex by doing 0 minus 12i. If you allow the real part to be 0, that would be written as, that could be written as a complex number. All right, so when you talk about complex numbers, we can add, subtract, multiply, and divide them. First thing we're looking at is adding and subtracting them. In doing so, all we will be doing is combining your like terms. So you add the reals to reals, imaginaries to imaginaries. Those are just examples of complex numbers. You say what's going on in the green. They were just examples of complex numbers. Yeah. All right, so if I have my 5 minus 11i plus 7 plus 4i, combining your like terms, you add the 5 and the 7 together. That'll give you 12. -11i plus 4i, -7i. All right. Same thing with subtraction. -5i plus -5 plus I minus the quantity of -11 minus 6i. So don't forget, you always distribute that negative that's sitting in front of the parentheses first. It changes each sign. So -5 plus I plus 11 plus 6i. Combine your like terms, -5 and 11 will give you 6. I plus 6i will give you 7i. All right, let's scroll up. All right, so let's look at multiplying complex numbers. So this right here is your original. We have 4i times 3 minus 5i. So we would distribute just like we would any other time we would have this type of scenario. And that'll give us 12i. 4i times 3 is 12i. 4i times negative 5i is negative 20i squared. All right, somebody asked me to go up a little. How far you want me to go up? Let me know. That's good enough. Okay. All right, so when you distribute, like I said, you have 12i, and then 4i minus 5i would be 20i squared. Now, let me see if I can do this. So now when you have I squared, we cannot have I squared as a part of our final answer. Our answer can always be simplified further if we have I squared involved. So if you look at what I have in the purple circle, don't forget that I represents the square root of -1. So if I were to square the square root of -1, the square and square root will cancel, and that will leave me with just -1. So even if you don't remember the process, you don't have to. I'm just showing it to you, but you have to remember that I squared simplifies to -1. I squared will always simplify to -1. All right. Am I able to scroll up now? I know somebody was still copying.
I have a question then.
Yes.
If I to the second power equals -1,
Mhm.
then in the problem that you solved in red, couldn't it be simplified further by multiplying that that -20 by -1?
Yeah, we're not finished.
All right.
Yeah. Somebody, I scrolled up for somebody, but you're on the right track, most definitely. Mhm. All right. So let me see if I can put it back. Somebody said, all right, thanks, sir. So like your classmate mentioned, that I squared turns into -1. Oh, erase too much. And so now I'm looking at 12i minus 20 times -1. And then that negative to a negative returns positive. That'll give me a positive 20. And then mentioning here, standard form, you put your real part first, then your imaginary. And then that'll be 20 plus 12i. All right. Any questions? Any questions before we do another one? All right. When you said -1 and not another number, are you talking about right here? You said, why do you use -1 and not another number? Because if you, for the square part, well, we're dealing with the imaginary. And remember, we talked about it initially. We're talking about I being equal to the square root of -1. So that's where the -1 comes from. Whenever you see I, it assumes you already know that that represents the square root of -1. So yeah, so I think hopefully that answers your question. But if not, feel free to ask away. So the next one we have 7 times -3i, well 7 minus 3i, sorry about that, times -2 minus 5i. So you would do your normal binomial distribution. 7 times -2, -14, 7 times negative 5i, negative 35i. Negative 3i times negative 6 will be positive 6i. Negative 3i times negative 5i will be positive 15i squared. Problem with distribution. Now we can combine our like terms in the middle. Negative 35i plus 6i. So essentially the square root of negative 25 would be 5i. Now, right, 1 times 1 is 1, so square root of negative 1 will also be 1i. Yeah, that's fine. Do what you're saying, yeah. And also square root, I squared, we already mentioned that turned to negative 1. So it means that it will actually be negative 15. And so negative 15 plus negative 14 is negative 29. So we have negative 29 minus 29i. Any problems with what we did there? $15 cancel out. No, the 15 combines with the negative 14. You have a negative 15 and negative 14. That gives you negative 29. So it don't necessarily cancel out. Okay, cool. All right. All right, so the next thing in this section they talk about is the complex conjugate that's going to help us with the next operation, which is division. So A plus BI and A minus BI complex conjugates of each other. So if I have 5 plus 3i, the complex conjugate of that is 5 minus 3i. And notice the only thing that changes is the imaginary sign, the imaginary numbers sign. That will be your conjugate. So if I have negative 8 minus 11, then negative 8 plus 11, negative 8 minus 11i, then negative 8 plus 11i will be the complex conjugate. And then if I just had 23i, negative 23i would be the complex conjugate. You change the sign of the imaginary part.
So what's a complex conjugate?
Say that again.
What exactly is a complex conjugate for?
Well, that's what we're about to get to. I was just introducing it first. So yeah, that's what we're about to get to next. All right. So notice that we've added, subtracted, multiplied, and divide complex numbers. We add, subtract, and multiply complex numbers. Now we're going to look into dividing, and that's when we're going to use our complex conjugate. All right, so when you talk about dividing by a complex number, or what they consider dividing by a complex number, we have 3i over 4 plus I. All right, so to do what they, like I said, consider multiplying by a complex, multiplying by a complex number, we're going to have to multiply the top and bottom by the complex conjugate of the denominator. So we have 3i over 4 plus I. So it means we're going to multiply top and bottom by 4 minus I. You said, what was the equation? I'm not sure what you mean. This is the problem right here. I don't know if that's what you're asking. So let me know. So that wasn't the problem. That was me introducing the term complex conjugate and what it means. So the complex conjugate is just having the opposite sign as far as your imaginary part. So that wasn't a problem. That was just me introducing the term, the terminology. All right. And then here is where we're going to actually use complex conjugate. All right, let's scroll up. Right, okay. All right, so don't look at this part yet. That's the final result. We're not there yet. So here's where we are. Going to multiply top and bottom by 4 minus I. So let's look at the numerator. 3I times 4 minus I. So we distribute 3I to each term. 3I times 4, 12I. 3I times negative I is 3I squared. Don't forget I squared turns into -1. So in the back, we have -3 times -1, which is +3. And then if we were to write it in standard form, the +3 would go first. So that's 3 plus 12I. So that's our numerator now, 3 plus 12I. Any problems with that?
I'm kind of lost. Could you like explain it again?
Lost with what part? What, you just talking about the multiplication right here?
Yeah, when you said okay, so when you said like it say multiply the top and the bottom.
Mm-hmm.
So then what's next after that?
So we multiply top and bottom by 4 minus I. All right, that was the conjugate of this. And so now you don't want to do it all at one time, right? So we just right now we're just looking at the numerator, and that's what we're doing right here.
Okay.
Mm-hmm. And so that, yeah, like I said, that's what the numerator. And then next we're looking at this part, 4 plus I times 4 minus I, and that's what we're going to do over here. So we distribute each term. 4 times 4 is 16. 4 times negative I is -4I. I times 4 is +4I. I times -1 is negative. Well, I times negative I is negative I squared. So 4I and 4I cancel in the middle, and then once again, I squared turns into -1. 16 minus 1 minus -1 is going to be 16 plus 1, which is 17. So that's our new denominator. 17 is our new denominator. And now we can go up here to finish it off. So 3 plus 12I over 17. New numerator, new denominator. But when it comes to writing complex numbers, they will want you to split up your answer. Leaving it like this wouldn't be considered standard form. So it will want you to take that 7 into each number, making your final answer this one right here. 3 over 17 plus 12I over 17, or 12 over 17I. All right, any problems? Can I scroll up? Give you guys a chance to break. All right. Last thing they introduce in this section is making sure that before you simplify or calculate, that you do take the I out first. And so don't think we had that situation up to this point. So in other words, if I have square root of negative b, then before I do any type of processing or operation with the square root of negative b, make sure I pull the I out and write it as I square root of b. So why is that important? I'll show you in this example here. So whenever you have the square root of two numbers and you want to multiply them together, you can just multiply what's under the radicals. If I were to take the square root of negative 25 times the square root of negative 4, if I just multiply what's under the radicals, negative 4 times negative 25 is a positive 100. Well, then the square root of 100 is 10. But that process is incorrect because it eliminates the presence of that square root of negative. So what I needed to do have done first was to pull the I out. So that's I square root of 25, I square root of 4. Multiplying those together now after I've extracted the I, that's the presence of that negative. Then that's I times I, which is I squared. 25 times 4 under the radical, which is 100. Now I have this negative 100 as a final answer versus positive 100, which was incorrect. All right. And so that's what we mean by taking the I out first. Also, we do recognize that because 25 and 4 are perfect squares, I could have simplified them all the way down to 5i times 2i, which is 10i squared, which is still negative 10. Either way, you'll still get the same answer, but I kept the radical here because I wanted to make sure we understood the radical process. Either way, you'll still get negative 10. Yeah. Not a problem, not a problem. Let me know when you're ready to go forward.
Can you actually solve that again now that I have it written down and I can watch what you were doing?
All you do is take the square root of each one of them individually. So you took the square root. Now it just depends on which way you want to go, whether it's this way or this way. Take the square root of negative 25, that's 5i. Square root of negative 4 is 2i. When you multiply them together, that's 5 times 2 is 10. I times I is I squared. And remember, we said I squared is negative 1. And so that's how we got negative 10.
Okay.
Yeah. So hopefully that was okay. If not, let me know. Okay, cool. Oh, yeah. I didn't even recognize it. You got the new mic.
Nah, I didn't realize that you had to click the settings for your AirPods instead of the computer mic. So
Gotcha.
technology, man. That
Yeah.
technology is too much for us old guys, man.
I thought that GoFundMe, man, that they were gonna put up for you. I thought it went through. I thought everything was good.
Hey, I'm still waiting on it, bro. I got tuition to pay, so y'all send it my way.
All right. So before we go to this next one, questions. Now, didn't mean to erase that. There you go. Don't copy this yet. We're gonna hit this red first because I want to make sure we understand what we can and cannot add or subtract. So just want to make sure everybody's okay. All right. So let's look at this red part first. So when we talk about adding, subtracting radicals, the index of the radical has to be the same. The radicand, which is what is under the radical, has to be the same as well. So when we look at this first one, 5 square root of 2 plus 3 square root of 2, we have the square root and we have 2 under the radical. And because that is the case, I can add the 5 and the 3 together to give me 8. If anything is different, then I cannot add them together. So when we look at the second one, I have the square root of 2 and the square root of 7. Because both of them are not the same under the radical, I cannot simplify those any further. Okay. The third one, I have 5 square root of 2. Then I have 3 cube root of 2. because the index of the radicals are different, I cannot add them together. And then for that fourth one is real and then one is imaginary. So I cannot add those together. So the only one I could add together was this first one. And that's because they had the same index. They both were real. They had the same index, which was the square root. And they had the same radicand, which was 2 under the radical. So that's the only condition that you can add and subtract your radicals. So just make sure we're okay with that thought process. Because when we go to this next problem over here, that's what we have to look for in order to be able to simplify further, or simplify to its lowest terms. All right, any questions on this over here?
You go over it just one more time. I think the jump from cube root to square root kind of tricks me up.
Okay, it's just saying that if you don't have the same index of your radical, you cannot add them together. That's all. So
Imaginary numbers count as an index.
no, that's different. So that's why it's a different example altogether. So we already talked about real and imaginary can't be added together. I was just making sure we held on to that. So your real and imaginary cannot be added together either. Like all three of these are three different scenarios that present to you as to, excuse me, as to why you cannot add or subtract, your expressions. So here, let me erase these again. All right, so here it was because of what was under the radical. Here it was because of the index of the radical, square versus cube. And then here is because one was imaginary and one was real. So those are three different scenarios, three different reasons why you cannot add or subtract your expressions, your terms, or your radicals. Right. So now I still have my eraser on. Okay. So now over here, in its current form, we cannot subtract these two numbers. And that's why I went through this first, because I want to make sure we understood why we couldn't do it here. So we cannot add or subtract these two terms in their current form. So now what we need to do is go back to how we originally introduced the section talking about breaking the numbers down all the way to see if in their simplest form, can we then subtract them? So looking at the square root of negative 18, I'll break that negative 18 up into negative 9 times 2. Then take the square root of negative 9, which is 3i. And of course, you leave the 2 under the radical. You cannot do anything with that.
Wait, why couldn't we do that one?
Do what one?
With the square root of negative 18 minus square root of 8.
Well, it's not a perfect square.
Oh, okay.
Yep. So, and that's the far. Oh, I keep leaving my eraser on. So that's the farthest you can go with that.
Okay.
And you do the other side, since negative 8 could be negative 2 times 4.
Well, I would do negative 4 times 2 because you can take. I always break it up into what I can take the square root of and what I cannot take the square root of. So I can simplify that negative 4 into 2i, and I'll leave the 2 under the radical. So the same thing I did here. I took what I can take the square root of, what I cannot take the square root of. So I took the square root of negative 9 that turned into 3i. And so that's how I normally break it up. All right, so before we go any further, is everybody okay with the two new pieces that we have? So this is our new problem, 3i square root of 2 minus 2i square root of 2. And now that we notice that both are, I keep leaving that eraser on. Both are imaginary, both are square root, and both have 2 under the radical. So, like I said, they all have to be the same, either both real or both imaginary, both have the same index on your radical, both have the same radicand. As long as all three of those match up, then you can go ahead and add or subtract accordingly. 3 minus 2 is just 1. And these are just the two different ways that you can represent the answer. I square root of 2 or square root of 2i. All right. So the next one, this is the original problem. -1 plus square root of -5 squared. All right. So before you do anything with it, remember we said we have to bring the I out. If you have a negative under your radical, you have to bring the I out. And so square root of -5 simplifies to I square root of 5. And now because it's being squared, we can go and expand that out. -1 plus square root of -1 plus I square root of 5 times -1 plus I square root of 5. From there, we'll FOIL. So -1 times -1 is +1. Then -1 times I square root of 5 is -I square root of 5. I square root of 5 times -1, -I square root of 5. Then I square root of 5 times I square root of 5 is I squared square root of 25. So, you know, I times I is I squared. Square root of 5 times square root of 5 is square root of 25. Make sure we're okay with the distribution.
So those two I5s combined to make two I5, or
Yes.
how
Yep.
about the
So just like having -1 minus 1 will give you -2. So we have -1I square root of 5 minus I square root of 5 minus 1I square root of 5 will give us -2I square root of 5. So those are our like terms in the middle. And then here, this simplifies because we have I squared, which is -1, and then square root of 25 is 5. So let's just in the chat. Sorry. Well, let's speak positive. Let's say that you're gonna hold on to it. Let's speak positive. So then after that, 1 minus 5, you have like terms of 1 and -5, which is -4. And so that would be your most simplified expression, -4 minus 2I square root of 5.
Real quick, the I next to, or the 2, is that an index next to the I? Where it's
Talking
square
about right
root of
here?
25? Up, the next one up.
Right here.
Yeah, is that index?
No, that's I squared.
Okay,
Mhm.
thank you.
Not a problem. Let me see if I can write that a little closer to the I. All right, questions before we look at, I think this is the last one out of this section. All right, so next one, let me see, I think it is, yeah, that's the last one for this section. So we have -25 plus the square root of -50 over 15. So once again, before you do any calculations or simplifications, we want to simplify this square root of negative first, square root of negative whatever we're dealing with. So here we have square root of negative 50. I can break up that negative 50 into negative 25 times 2. Square root of negative 25 is going to be 5i, and then you leave 2 under the radical. And so that gives us this new expression right here. Oh. All right, so we have negative 25 plus 5i square root of 2 over 15. So that's as simple as it gets in the numerator. But now we can break it up by sending that denominator into each term. Because remember, if we're going to write it in standard form, they expect you to break it up, real part and imaginary part. So that's negative 25 over 15 plus 5i square root of 2 over 15. Simplify that. They have 5s that are in common with each. And that'll be negative 5 over 3 plus I square root of 2 over 3.
Huh. So. Okay. You simplified it.
Mm-hmm. Mm-hmm. All right. Any other questions on that?
So 5 times 25. 5 times 5 equals 25. 5 times 3 equals 15.
Mm-hmm.
That equals 5 times 1 equals 5. 5 times 3 equals 15.
All right. Any questions? Any questions? Did somebody say sadness? Was that?
Oh crap, I'm unmuted.
That's funny. I think I heard some other words too, but it's all good. Well, maybe we don't need to do any of 1.5 today since I'm bringing sadness to the world. Oh man, that was funny. Okay, well, I can we can start 1.5 next class. It's not a big deal. I'll give you a chance for you guys to process 1.4. Any questions or anything before we close out today?
I got a question about an older assignment that I can ask like after everybody leaves.
Okay.
I don't want to hold anybody up.
Yeah, it's not a problem. Anybody else have any general questions? Yes.
I remember you said before, like on the first day, that how you would count us working is by doing stuff on MathLab.
Mm-hmm.
Are you talking about like the homework assignments or something else?
Yeah, the homework.
Okay.
Mm-hmm.
Got it.
Yep. All right. So with that being said, we'll go ahead and pause right here. If you want to stay back for those questions, see what they have, then that's cool. If not, you are free to go, and I'll see you on next class. We'll get started at 1.5.
Have a good day.
You guys have a good one. Take care. Thanks.
Bye.
All right, let me see. Trying to find scratch work. So I don't have one. Let's go here.
I actually had a question.
Mm-hmm.
So I can't. I think it was last class or class before last. I need your help on like a problem on homework that I was stuck on.
Mm-hmm.
So I'm kind of still confused. I'm kind of still lost about when we was doing the, I think it's called the trying to we had to find the LCD.
Mm-hmm.
Yeah, I'm kind of lost. Like I don't understand that.
Well, you got a problem?
Yeah, hold on. I'm gonna find it. I'm not gonna go to it.
Okay. While you do that, Mr. Williams, what did you have?
So I have a feeling I just completely missed this part of your assignment during the first one. So on
Mhm.
1-2, when you get to question 8, it says to solve for 0.
Mhm.
And I do not remember going over that at all. And I don't have anything like in my notes that even like references that. So I have a feeling like I just completely missed it. And yeah, I am struggling with that because I just don't understand what the actual concept is. I can give you the problem that was given to me.
Okay. Yeah. Go ahead. You can go ahead and do that.
All right, so it was x plus 5 over 3
Mhm.
equals 3 minus x plus 4 divided by 2.
3 minus x plus 4. Now it's like that.
Correct.
All right. And it says solve for 0.
If you give me just a second, I'll tell you exactly what it says. Because I was solving it for x without having completely read the question properly. And obviously that's what prompted me to read the question better.
Mm-hmm.
So, oh, it's making me sign back. So the question,
Yeah.
it says, the following rational equation has denominators that contain variables. For this equation, A, write the variable or values of the variable that make the denominator 0.
Mm-hmm.
These are the restrictions on the variable B. Keeping the restrictions in mind, solve the equation.
Right. Okay. Yeah. That's what I thought. Now you said this was number what again? 8?
I think it was number 9.
Number 9.
Yeah, it was number
Yeah.
9.
Now let me go back to what you told me. Now you may have, this one looks like number 8. Oh, let me.
Oh, did I? Oh, you know what? You might be right.
Yeah, but I think number 9 has variables in the denominator.
Hang on, I got it. Let me pull it right back up.
Yeah, so now
It
number
is
8 is just, you were
Yeah.
right to just find a solution, but number 9 should have had
correct.
a little more to it. Okay.
I'm sorry, I'm on the wrong page. So
Okay.
the problem is 3 over x
All right, hold on 1
plus
second.
3
3
yeah.
over x plus 3
equals 2 over 3x
Mhm.
plus 28 divided by 9.
Like that.
3x plus 3 equals, yes, correct.
Okay. So now the first part, they want to know what are the restrictions. We talked about it. I didn't make it an actual problem, but I said that wherever your 0 is, whenever your denominator turns into 0 or can be 0, that's when you have your restrictions. So what you do is you take your denominator, set it equal to 0, and then solve. So each one has a variable. So in other words, if I had, let's say if I had x plus 3 in my denominator, then I would have x plus 3 equal to 0. Whatever's in your denominator that has a variable, you set that equal to 0 and then solve for it. And those would be your restrictions.
Okay.
So this is the
Okay.
same issue I was sticking around for because I'm having the hardest time grasping this concept. I've watched so many YouTube videos. I can't even tell you. And I just don't get it.
Ms. Dawn, I think
Don't
you're
get
making it more
upset.
harder. I think you're making it harder
Don't
than
get
what it is.
upset. Dawn, my girlfriend is in a master's program for finance right now, and she was getting her butt kicked by this the other night, and she was all sorts of bent out of shape about
Yeah,
it. So don't
I
feel
cannot
bad
grasp
at all.
this concept.
Yeah.
I just don't get it. I even got the question wrong on the homework and I was like,
Mhm.
fuck it, because I just can't.
All right. So this is what we do. I think what y'all doing is making
All right.
it way harder than what it is. All you do is take the denominator, set it equal to 0, and solve for x. That's it.
That doesn't make sense to me.
Well, now what you're saying is now when you're talking about mathematically, if I set something equal to 0, let's say if I have x plus 5 equal to 0, when I solve this, I'm asking myself, when is this equal to this? So you want to know, because remember, the whole premise is I do not want 0 in my denominator. That's where all of this is circling around. So you're asking yourself, when is my denominator equal to 0? Because I don't want that to happen. So I don't want my denominator to equal to 0. So if I have 4 over x plus 5 minus 7 over x plus 10 equal to 9. I don't know. If I solve this, the first thing I want to do though, before I do that, when are these two going to be equal to 0? Because if x ends up being that, I have a problem. So in other words, x cannot be equal to -5, because if x is equal to -5, that's going to give me 0 in my denominator.
Right.
You see that?
Because the
Or-
negatives equal the positive.
right. Same thing if x is equal to -10, that's going to give me 0 in my denominator. Give me 1 second.
So essentially solving for x is just
Say
gonna
that again?
be making it the opposite.
Yeah. Mm-hmm.
But I did that on one of the problems and it told me I was wrong.
Now you guys
That
have
was-
to tell me what you know what
I
problem
have
that
no
was?
idea which one it was.
So let me
It's
make
the
sure
only
I'm
one I
right.
got wrong.
I'm sorry. So let me make sure I can. So now that I understand that I'm setting my denominators to 0,
Mhm.
so I would actually write this out. Would it be 3x equals 0 plus 3? No, that can't be right.
No.
It was actually question 10. I got half of it right, half of it wrong.
All right, we'll check it out. So
And
this
I got
one,
the first part wrong.
all right. So I'll take a look at it and see what you got going on. So here, x equal to 0 is just that, x equal to 0. Now here, 3x equal to 0, you divide by 3 and end up getting the same thing, x is equal to 0. In other words, if I were to plug 0 in right here, 3 times 0 is 0. Now I have 0 in my denominator, which is what I do not want. Or if I plug 0 in right here, 3 over 0 is my fraction, which is what I do not want. So it's all about what is going to create 0 in my denominator and give me a problem.
But I think I see what I did wrong. I
So
think
in
the
this
first
case,
one. Okay.
you're saying that we're trying to find 0 in this case because 0 is the number that creates 0 in our denominator, which is what we're trying to find
Yes. In
as
this
the
case.
problem, correct?
Yes, exactly. Mhm.
So, okay, can you do one where 0 wouldn't be, and we would actually have to do something? Because now that you simplified it like that, it makes a lot more sense.
Mhm.
So
So yeah.
if we
So
could
going
just
back,
do something that a
yeah.
little more complex.
Yeah, going to this one right here, I would set x plus 5 equal to 0 and x plus 10 equal to 0. Subtract 5 from both sides, x is equal to -5. Subtract 10 from both sides, x is equal to -10. So these are the two values that I cannot use.
Okay, so you would actually have to write both of those out for the
Mhm.
correct answer.
Right,
Okay.
right. Mhm.
Okay.
So
Now,
if they
remember-
don't equal the same,
No, they don't.
If
No, it's not,
they're-
yeah, it's not going to always be the same. It depends on what you have as your denominators.
okay, so if they both denominators don't equal the same to make it 0, then that's when you have to plug it in.
Well, you'll have,
Yeah.
well, see, now remember, these aren't your solutions. That's what I was going to go to. Remember, these aren't our solutions. These are the values that cannot be solutions, because when x are these values, I get 0 in my denominator.
Okay.
Yeah. And so it
Which
just, so
for this particular question is what we were asked, is it not?
right,
We were
exactly.
asked to find,
Yes.
okay. I was just
Mhm.
making sure that I was on the same, okay.
Right. These are your restrictions.
So if 0 is the answer for both, do you have to put 0 in twice in the answer, or can
No.
you just put 0 in once?
Yep. 0 once is fine.
Okay.
Mhm.
Man, my girlfriend's gonna be so pissed when I show her how simple this is.
That's what I said. I
Oh,
think y'all were just
boy.
making it more complex than what it was. It was just setting it equal to 0, solving whatever your denominators are, set each one of them individually to 0 and then solve it. And those are your restrictions. Yep. All right.
That makes more sense, man.
Cool. I know, Miss Stewart, did you find that problem?
Yeah, I found it.
All right, what you got?
It was 5x over 3 minus x equals x over 6 minus 3 over 2.
Got to write it down right.
Mhm.
So 5x over 3 minus x equal to x over 6 minus 3 over 2.
Yeah, that's it.
Okay. So your LCD, you said you had a problem with the LCD part. Your LCD is the smallest number that each one of these can divide into evenly. And that's going to be 6. Because 3 can divide into 6, 6 can divide into 6, and 2 also can divide into 6. So you
Okay.
want the smallest number that each one of them can divide into evenly. Now,
Okay.
let's say, go
I
ahead.
understand that part, but it's like after this, like when you say multiply the LCD by each numerator, right?
Mm-hmm. Right.
Okay, so all right, let's see.
Yeah, I'm listening. I was just writing while you were talking.
Oh, that's it. Like that's where I have a problem with when it's time to multiply them. Then I get stuck. Like I don't
Mhm.
know.
All right, so that's cool. So see how we multiply each one of them by 6. Even if it doesn't have a denominator, you're still going to multiply each one of them by 6. You have to multiply each term by 6, or you're going to change the value of the problem. Okay. So 3 divides into 6, and that leaves you with 2 now. So that 2 times 5 is going to be 10x.
Wait, so are we? Wait, hold on.
Mhm.
Okay. Are we multiplying the denominator by 6 or the
Nope,
numerator?
just each numerator. We multiplied across the equation. We didn't go up and down. We didn't do top and bottom. We multiplied across the equation and multiply each term by 6.
And it's important that you bring each numerator or denominator down in order. You don't equal those out to 6, because I
Right.
made that mistake and
Keep
got
'em.
all sorts of jacked up. So you keep
Mhm.
actually the denominator per one, otherwise it will completely mess your problem up.
Right, right. So, yep, the 3 is still there, the 6 is still there, and the 2 is still there. Yep.
Okay.
And then from there, each one of your denominators should be able to divide now into the numerator. 3 goes into 6 and leaves you with 2. So 2 times 5 is 10. This would just be 6x. The 6 couldn't cancel out with anything. There's nothing down here. So that's just 6x. 6 cancels completely.
Oh, so once we got the equation like that, are we getting rid of the denominators?
Yep. Because the
Okay.
denominators can divide into the numerators. Yep.
Okay.
Yeah. As a matter of fact, that's the whole purpose of doing this, so that you can get rid of the denominators.
Okay.
Yeah.
Okay, so that's why I was getting stuck on. I didn't know what I was doing with the denominator. Like I was getting confused.
Okay. Yep.
That's why I said to make sure you bring that actual denominator down in succession, because I was
Mhm.
making the mistake of trying to simplify, like, oh, wow, well, we found a lowest common denominator and we found that number to be 6. So why not make 6 the bottom number? But like I said, it completely messes up the math. And
Oh yeah.
I learned that the hard way.
So, Ms. Stewart, you good now?
Yep.
Okay, cool. All right. Anything else? Anybody else before I get ready to roll on to this next class?
That's it. Thank you.
Not a problem.
Yeah, appreciate it, man.
Not a problem. Glad we were able to bring that clarity. All right.
Thank you.
Not a problem, man. I'm glad you got it this time, because I know we didn't get it last time.
Man, I've been struggling since day one with that concept. I'm like, what the hell?
You ain't
Had me
alone,
crying
trust
last
me.
class, and then I was like, oh wait, this is not that hard. Okay, I got it.
All right.
Hey,
then.
at least I don't feel like having a drink at 10 o'clock this morning after this class.
For
It's getting
real.
better,
This
right?
last one.
It's getting
I was
better.
like,
So,
shit, should I drop the
we're
class?
getting
Is
better.
it too late?
Look, we got the mic connection straight. We don't need a drink. Everything's
Yeah.
getting better.
That's right. We're on the come up now.
Right. Y'all have a good one.
All right,
All
I'll
right,
see
man. We'll
y'all
see
in
you
a few
on
days.
Wednesday. Y'all have a good one.
Take
All
care.
right, bye.
Bye.